Let's look at zero pole meshing equivalence. So in this method, what happens is that you're trying to match the poles and zeros from S plane into Z plane. So it says poles and zeros on the S plane can be mapped to poles and zeros on the Z plane using Z is equal to e to the power st. So if h of s has a pole at s is equal to minus a, then h sub zp, and zp here refers to zero pole, the method, h sub zp of z has a pole at z is equal to e to the power minus 80. So we map the poles using this equation. So that's number one. Number two, if h of s has a pole at minus a plus jb, then h zp of z has a pole at r times e to the power j theta, where r is equal to e to the power minus 80 and theta is equal to bt. So basically just substitute minus a plus jb into this equation in place of s. Now if h of s has a 0 at s minus a, so now moving on to the zeros, then h sub zp of z has a 0 at e to the power minus 80. So again, this is for zeros. The zeros of h of s at s is equal to infinity, that is when the numerator of h of s is a constant. So are mapped in h sub zp of z to the point z is equal to minus 1. Right, so the gain should be scaled so that the frequency responses match at some desired frequency, typically zero frequency. So what we do in this case is set s to 0 and then try to match the result with by setting z to 1, because if in the equation z is equal to e to the power st, if s is 0 then z will be 1. So example, if h of s is equal to a over s plus a, number one, the poles. So the poles are the denominator polynomial equal to 0. So in this case, there is only one pole, which is at minus a. So the pole at s is equal to minus a maps to z is equal to e to the power minus 80. So my equation, my z transformation h of z will have a pole at e to the power minus 80. There is a 0 at s is equal to infinity because the numerator is a constant, and that maps to z is equal to minus 1. So considering all this, there is a pole at z is equal to e to the power minus 80, and there is a 0 at z is equal to minus 1. So basically what I get is z plus 1 over z minus e to the power minus 80, and that multiplied by a constant k. So now we have to solve for k, and the way we can solve it is for k is by using this statement. So we, in our h of s equation, we just set s, if we set s equal to 0, then h of s will be equal to 1. So that's what we do here. H when s is equal to 0 is equal to 1, and then when s is 0, z should be 1. So we substitute z is equal to 1 in this equation. So when we substitute z is equal to 1 in this equation, we get k times 2 over 1 minus e to the power minus 80, and that is equal to 1. So that will give us a k of half times 1 minus e to the power minus 80. And now we can get our h of z, the full form, including k, which is half 1 minus e to the power sorry, half into 1 minus e to the power minus 80 times z plus 1 divided by z minus e to the power minus 80. So it says an alternative is to map 1 0 at s is equal to infinity into a 0 at z is equal to infinity. So if we do that, this introduces a unit delay. For example, to give the computer time to compute the output calculation. So if we do that, then instead of having a 0 at z is equal to minus 1, we will have a 0 at z is equal to infinity. So instead of having z plus 1 in the numerator here, we will just have 1. So what this equation will become is this, which is h of z is equal to k over z minus e to the power minus 80, and then we can solve for k. So if we substitute this equal to 1, then we get k as 1 minus e to the power minus 80. So that is when we substitute z is equal to 1 and equate this equal to 1 using the same method described in 3 here. So then if we do that, then we will get k as 1 minus e to the power minus 80, and that then the full form of h of z is this 1 minus e to the power minus 80 divided by z minus e to the power minus 80.